Why are the world's most efficient solar panels learning to sweat? When it comes to solar, you'd assume more sun equals more power, but the truth is that solar panels actually hate being hot. In fact, for every single degree the temperature rises, these panels lose up to 0.5% of their efficiency, and in the deserts where we're building our largest solar farms, that can mean an 18% performance drop. But scientists have figured it out by borrowing from nature's playbook. They're using the same cooling trick that makes humans so good at staying cool. Solar panels can effectively sweat using hydrogels, and the results are staggering. One application of hydrogel allows for both efficiency boosts and extended lifespans, no moving parts required. How is this possible, and is this extra juice worth the solar squeeze? So, scientists have figured out how to make solar panels sweat, just like humans do. Researchers from Thailand's VISTEC, Saudi Arabia's KAUST, and teams at Princeton University have all made exciting advances using special water, absorbing materials called hydrogels that soak up moisture at night and slowly release it during the day to keep panels cool. The results are impressive, but the big question you might be asking yourself is, what's the problem they're actually trying to solve? Here's something that might shock you. The hottest days of summer are when your solar panels perform their worst efficiency. Why is that? For every single degree Celsius or 1.8 the surface temperature climbs, your panels lose 0.2 to 0.5% of their efficiency. On blazing desert days, that can mean an 18% performance drop. It's a pretty heated issue, literally and figuratively. But why does heat hurt solar panels? They don't actually convert heat into electricity. There's a complicated game of billiards happening beneath those surfaces. Sunlight knocks electrons and holes loose, hopefully sinking them into the pockets. That are the solar cell's junction to produce electricity. If any step goes wrong, then no charge for you. Heat makes everything bounce around more, so those electrons get harder to control before they crash back into other particles. Now, measuring exactly how hot panels get is tricky. Studies often measure from the back rather than the sun, facing surface where temperatures are highest. But even with measurement uncertainties, cooling panels by just a few degrees can yield significant efficiency gains. So how do we cool them down? We could use the same approach as computers and data centers, but there's a catch. Active vs passive cooling, you might be thinking. Why not just strap some fans or water pumps to these panels? Active cooling works great for computers and data centers, but here's the problem. Active cooling uses electricity, and when your solar panel is already struggling in the heat, the last thing you want is a cooling system that eats up more power than it saves. It's like running the air conditioning with all the windows open. So what's the alternative? Passive cooling, no moving parts, no electricity required. Think heat sinks like vents, or in this case, hydrogels. Passive systems are generally less powerful than active ones, but they have a huge advantage. Once installed, they just work for decades without maintenance. For solar panels that need to sit on rooftops for 20 to 30 years, that's exactly what you want. The challenge is figuring out how to make passive cooling work for solar panels. We've been designing passive cooling systems for buildings for centuries, but PV are a different beast entirely. The answer: enter hydrogels. These polymer-based gels may be the perfect passive cooling solution. They're porous and permeable, which lets them absorb water at night and slowly release it during hot days. This might sound futuristic, but hydrogels have been around since 1894. You may eat them regularly. The gelatin in your food is a hydrogel, and they're used in everything from medicine to diapers to wine making. Here's how they work for solar panels. You apply a thin layer to the back of the panel, and they automatically start sweating. During cool nights, they soak up moisture from the air. When the sun heats up the panel during the day, they slowly release that water, cooling the panel through evaporation. It's basically the same trick that makes humans some of the best temperature regulators on the planet. Our sweat can dissipate nearly 1,000 watts of heat. Why not steal this incredibly successful biological technique and put it to work cooling solar panels? Let's start with the breakthrough from Thailand's VISTEC. They've created a hydrogel that dropped VISTEC Hydrogel solar panel temperatures by 23°C. That's from a scorching 70°C down to a much more manageable 47°C. That massive amount of cooling translated directly into a 12.3% efficiency boost. But here's what makes their approach brilliant: weight. While other cooling systems can add hundreds of pounds to a solar installation, VISTEC's hydrogel weighs just 11 pounds per square meter. That's 80% lighter than competing technologies like phase change materials (PCMS). When you're installing solar panels on rooftops or shipping them around the world, every pound matters for both costs and structural safety. How do they pull this off? Their hydrogel uses two key components that work as a tag team. The first layer is a highly temperature-sensitive switch or gate. It opens up when the solar cell gets too hot, allowing water out to cool the cells. It also closes when it gets too cold out. The second layer is like a super-powered sponge that's incredibly good at absorbing and holding water. Together, they create a system that automatically regulates panel temperature without any human intervention. The results speak for themselves. In head testing against simpler hydrogel designs that lack that fancy automatic garage door, VISTEC's dual-layer approach was the clear winner. Even better, the school's industry partners are so impressed they're already talking about bringing this technology to market. That's the kind of enthusiasm that suggests we might see sweating solar panels sooner than expected. Now, VISTEC's breakthrough is impressive, but there's another research group with an even more surprising approach, one that's been tested in both the blazing Saudi desert and the freezing winters of upstate New York, with results that could make panels last over 200% longer. But before we dive into that, let me show you something about how we get information on these renewable energy advances. Depending on where you read about solar innovations, they're either revolutionary breakthroughs that will transform energy, or just another overhyped green tech bubble. When stories mix cutting-edge science, billion-dollar investments, and climate claims, how do you know now? Speaking of getting the full picture, let's look at that research I mentioned that's been tested in completely different climates. Researchers at Saudi Arabia's KAUST have been perfecting their own approach for years, KAUST Hydrogel, with impressive results. In the brutal heat of the Arabian desert, their hydrogel achieved an average temperature drop of 12.5°C22, 5F. The best cooling performance they achieved was 14.1°C25, 4F. I just threw a lot of numbers at you, so if that was confusing, here's the takeaway. In testing, KAUST Hydrogel boosted panel efficiency from 13.1% to 14.7%. That's a solid 12.2% performance jump. But here's what makes KAUST's work especially compelling. Researchers didn't just test in the Saudi desert. They also ran trials in chilly upstate New York to see if their cooling system could handle different climates. While the cooling benefits weren't as dramatic in New York, the long-term testing revealed something even more valuable. Panels with hydrogel cooling lasted over 200% longer than unprotected panels. That durability boost is huge for the economics. KAUST estimates their hydrogel could reduce the levelized cost of energy, basically the total cost per unit of power over a panel's lifetime, by 18%. Lower costs and longer lifespans. That's exactly what the solar industry needs. There's one more neat trick. Their hydrogel bonds so strongly to surfaces that you can retrofit it onto existing solar installations. Instead of replacing entire solar arrays, you could potentially just add this cooling layer to breathe new life into older, less efficient panels. I'd love to add something like this to my solar panels. Drawbacks: this all sounds pretty impressive, so naturally, the skeptical part of your brain is probably kicking in right about now. I know, because you remind every week. And it's right to do so. There's a lot to be excited about, but there are some drawbacks too, and a lot more research to be done. The first is the most common one, and one that longtime viewers are already very familiar with: commercialization. Technological advancements that look great on paper, great on the lab bench, and even great in prototype testing, like our solar gels, often find it hard to cross that final gap into the market. There's a myriad of reasons for this. Manufacturing is hard, scaling up is hard, and managing supply chains is hard. There are often unforeseen difficulties, if not big flashing weak spots, that only appear at the very end of the process. Solar hydrogels do have a bit of a leg up here because they're starting to move beyond the bench with some promising real-world tests, but I wouldn't bet on them just yet. The path to mass market is winding, lengthy, and unpredictable. Deeply intertwined with that issue is cost. While many of the organizations we've talked about today mention the cost-effectiveness of their materials, it's still an additional expense on top of typical solar installation costs. That extra expense may boost efficiency, and there is a return on investment. Still, how many cash-strapped upgrade Hesitant utility companies are going to spring for all the bells and whistles. Would homeowners want to spring for it? While hydrogel costs are decreasing and they're cheaper than active cooling methods, it remains to be seen whether they'll be cost-effective at industrial scale. Are these hydrogels liquid enough to be worth it? Only time will tell. Speaking of time, that brings us to the lifespan question. Early tests have researchers and their commercial partners excited, but hydrogels do dry out over time, dropping their performance. Much like batteries, what kind of performance falloff is acceptable? How long will they stay good for? What will 30 years of swelling and sweating cycles do to the modules, including their frames? As one KAUST researcher put it bluntly, if the current material can't last for 2 years, we'll have to work on another one. Another consideration is how much water gets absorbed without being released again easily. Some of these structures do such an efficient job of trapping water that they can't easily release it again. You can wring out a washcloth, but you can't exactly give the hydrogels stuck to the back of a solar panel a proper squeeze. And good luck explaining to your neighbors why you're out there trying to do that in the first place. Finally, while early tests are promising, how well will these panels handle weather extremes? I'm not just talking about desert heat or eastern seaboard chill. What happens when a blizzard rolls through Buffalo? Can hydrogels stand up to repeated freeze and thaw cycles? Can they be revived from a drought? For instance, evaporative coolers are often used in regions like the southwestern United States because that's where they're most efficient. Consider what it's like going for a run in Florida versus Arizona. The sweat feels more effective as a cooling source when your body isn't swimming in humidity thicker than flan. In short, there are a lot of known unknowns right now. Outlook. So where do we stand with sweating solar panels? Using NASA's dandy technological readiness level system, the hydrogels we've seen today are solid 7 successfully tested prototypes that work in real conditions. You could even argue KAUST's version hits an 8 with months of testing in both blazing Saudi Arabia and chilly upstate New York. Here's why industry partners are champing at the bit to commercialize this technology by the numbers. Let's use the median efficiency boost per temperature reduction of 0.5% or 0.005 as a decimal. As you know by now, cooling changes total efficiency. So for a temperature reduction of 20 degrees C, you get 20 degrees C times 0.005 or 10% efficiency increase. But PV don't exist in a vacuum. So let's factor in system size and electricity costs. Let's say we have normal uncooled panels producing 700 kWh a month at $0.15 kWh. This is worth $105 monthly, pretty typical for residential PV. Add hydrogels in ideal sunny conditions, think Arizona, not Seattle, and that 700 kWh becomes 770 kWh, worth $115.50 monthly. That's not life-changing money, but it's a nice bonus that pays for itself over time. Scale that up to industrial level, though, and the math gets more exciting. A large facility that generates 1.000 kWh a month, 1.000 MWh could potentially save around $15.00 monthly in the same best-case conditions. I want to stress this is our own analysis assuming optimal conditions. Location and local electricity costs will make these numbers vary by a lot. For instance, where I live you'd be looking at about $0.30 per kWh. But even half those savings would make hydrogels attractive to big solar operators, and that's not factoring in the benefit of extending panel lifespan. The bottom line, hydrogels look like a reasonably cheap and easy way to boost solar panel performance. These aren't pie-in-the-sky lab experiments anymore. They're tested technologies with industry backing and pathways to market. There's still more research to be done, and that's perfectly fine. That's how science works. But what we have so far is very cool, if you catch my drift. These developments are really gaining traction, or should I say soaking it up. The question now isn't whether hydrogel cooling works, but how quickly it can scale up to meet demand. But what do you think? Is this kind of passive cooling the way forward, or are these porous polymers never going to gel? If you want to see how these same hydrogels can literally pull drinking water out of thin air, and why that might hit the market before sweating solar panels, check out the extended version on Patreon where we explore the surprising dual life of this technology, and a big welcome to new supporter plus member Doug Strain. If you'd like to join, the link is in the description below. Be sure to listen to my follow-up podcast Still TBD, where we'll keep this conversation going. Keep your mind open, stay curious, and I'll see you in the next one.